Here we provide further evidence that resonance stabilization could not be the only force responsible for that unusual stability that benzene exhibits. If you look at these three compounds, they are all conjugated systems. They have pi bonds, pi electrons. But let's examine how they are different. So, of course, cyclobutadiene has 4 pi electrons. Once again, if you don't remember from the last chapter, remember a pi bond has 2 pi electrons. So you have 2 pi bonds here. The double bond, remember, is a pi and a sigma bond, and each pi bond has 2 pi electrons. This one turns out to be extremely unstable. So even conjugation doesn't make a difference here. So it's extremely unstable. Whereas when we look at benzene, we have 6 pi electrons. Once again, each is 2 pi electrons, 2 pi electrons, and then 2 pi electrons. So that's a total of 6 pi electrons. This one, as we said, has an unusual stability. And of course here, if we have cyclooctatetraene, we have also a conjugated system. We have 8 pi electrons, but we see no special stability. Worth mentioning, it reacts normally. So there must be something going on other than resonance. They all have resonance. All have resonance. Resonance, resonance, and resonance. Even a relatively large molecule such as aniline has an unusual stability. Because it's considered aromatic. But how do we know what's aromatic and what's not, and what is that extra stability? Now, we're not going to belabor this because this tends to be very complex, but it is worth mentioning. You might have covered this in a previous class, depending on the school you went to. There's a theory called molecular orbital theory. So it actually is like valence bond theory with hybridization, but it's actually more complicated. It's quite useful. One way of looking at it, just really quick, briefly, and I'm not going to test you on this, is that you have all bonding molecular orbitals filled. There's a closed bonding shell, which is energetically favorable and accounts for the special stability associated. There's something called Frost's circle. And you can think of it this way, that you have the bonding molecular orbitals, and you have the anti-bonding on the top. Anti-bonding, in a way, you can say they're bad for the system. They cause the system to be less stable. However, if you have all of your electrons in bonding orbitals, bonding MOs or molecular orbitals, then that's incredibly favorable, and it ends up lowering the energy of the system. So that's the idea. If you would like in class to learn more about it, I could share a video or two about that. But again, I am not testing you on that. But that's actually the stability that is associated with aromatic compounds, is they tend to be, their electrons tend to be in the bonding molecular orbitals, and they are completely filled. Think of like electron configurations where they were all filled. Now, to bypass all of that, all we need to do is to remember this important rule to discern a aromatic compound from a non-aromatic, and then there's of course a third class that is called anti-aromatic. So it's pronounced Huckel's rule, or some in the US here we can call it Huckel's rule. Huckel's rule states that any conjugated monocyclic polyene is a multiple double bonds, that is planar and has 4n plus 2 pi electrons, 4n plus 2 pi electrons, with n equals 0, 1, 2, etc., will exhibit the special stability associated with the aromaticity. However, systems with 4n pi electrons are anti-aromatic, and they are less stable than open chain counterparts. So these are the least stable, and the aromatics would be the most stable. Now, students oftentimes they look at this 4n plus 2 pi bond electrons, and then they get confused. There's no need to. I'm going to summarize it when we get to that in a second. But let's look at what are the criteria needed to count a molecule as aromatic or not. Well, it has to satisfy all of these 4 criteria. So number 1, the structure must be cyclic. You need a ring. Number 2, each atom in the ring must have an unhybridized p orbital. You're aware of that, so this was the conjugation. So chapter 16 is crucial for this chapter. So make sure you go back and review conjugation. The structure must be planar to allow for continuous overlap of parallel p orbitals. Absolutely, you have to have a planar structure, because you can't have say a rigid structure where there's no overlap possible. So you have to have a planar structure. And I usually help you with this so that you don't have to really go through a lot to find out whether a ring is planar or not. And then finally, 4 is the delocalization of the pi electrons over the ring must result in a lowering of the electronic energy. So if you satisfy 1 through 3 and then 4, which is Huckel's rule, then that is considered aromatic. However, if you satisfy 1 through 3, but 4 is not satisfied because you have 4n pi electrons, then that's considered anti-aromatic. So this is really, really crucial. They all seem a lot as of right now, but when you start doing them, they are very straightforward. Now, what happens if you don't satisfy one of these rules? So is there something other than aromatic and anti-aromatic? Yes, there is something called non-aromatic. And non-aromatic compounds, let's put it this way, non-aromatic compounds are neither aromatic. Let me just clean up my handwriting here. Are neither aromatic nor anti-aromatic, meaning if they are not, they don't satisfy, even if they satisfy, let's say, 1, 3, and 4, but they don't satisfy 2, then these would be non-aromatic. So something like if they satisfy criterion 1, 3, and 4, but not, just giving you an example. So this is not the only one, but not 4, but not 2, then this would be non-aromatic. Once again, as I said, this is very, it will be actually not bad when you do them. Now, before I continue, let me tell you what I mean about the 4n plus 2 electrons. And then in another video, we'll work on these examples again. When it comes to the 4n plus 2 electrons, you would like to do the following. So I'm going to erase here and then show you what I mean. Okay. So you would like to kind of like create a table here. And then put n, that's an integer. So n is an integer. We're not doing any fancy math here. You will pick it up in a second. And then you have a 4n plus 2 here. And then we'll do one for the anti-aromatic, 4n. Pi electrons. Pi electrons. Okay, so let's look at that. If you have n equals 1 and you plug in for n, then you will get 6 pi electrons. So if n is equal to 1, then you will have 6 pi electrons. If n is equals to 2, then 4 times 2 is 8, plus 2 is 10. So here, I'll do the first one for you. 4 times 1 is 4, plus 2, that's 6 pi electrons, which is what you see in benzene. If you have 3, then 4 times 3 is 6. 4 times 3 is 12, plus 2 is 14, and so on and so forth. So if you have 4, that would be 18. So you notice here that they increase by 2. So this is your aromatic criteria. You have to have 6, 10, 14, or 18 pi electrons. For non-aromatic, you of course see the difference is that if you have 1, then 4 times 1 is 4. If you have 2, then 4 times 2 is 8. Then if you have 3, 4 times 2 is 12, and so on and so forth. And again, they also increase in this case. Oh, sorry, we made a mistake here. We should go back and say they increase by 4 pi electrons. My apologies. Here they increase by, there's of course, a difference here because it's a different function. So this would be your anti-aromatic. And then this would be your aromatic. So absorb this, and then in the next examples, we'll go over them and you will be able to see them clearly.